The Big Bang Theory proposes that the universe originated from a singularity, a point of infinite density and temperature, approximately 13.8 billion years ago. But what caused this massive explosion, and how did our vast universe emerge from such a tiny, concentrated point? One leading theory suggests that the universe underwent a rapid expansion known as cosmic inflation. According to this theory, a tiny fraction of a second after the Big Bang, the universe expanded exponentially, stretching out its fabric and smoothing out irregularities. This rapid expansion helps explain why the universe appears to be homogeneous and isotropic on large scales. Another aspect of the Big Bang Theory involves the concept of cosmic microwave background radiation. Around 380,000 years after the Big Bang, the universe had cooled enough for neutral atoms to form, allowing photons to travel freely. These photons, released during a period called recombination, permeate the universe as the cosmic microwave background radiation. Detailed observations of the cosmic microwave background radiation have provided valuable insights into the early universe and its composition. Scientists have been studying the origins of the universe through various methods, including cosmological observations, theoretical models, and particle physics experiments. One such experiment is the Large Hadron Collider, where scientists recreate the high-energy conditions of the early universe to better understand its fundamental particles and forces. While the Big Bang Theory has gained significant supporting evidence, there are still unanswered questions. For example, what triggered the Big Bang? Why did the universe begin expanding in the first place? Scientists continue to explore these mysteries, and ongoing research aims to refine our understanding of the earliest moments of the universe's existence. The mysterious realms of dark matter and dark energy, two enigmatic phenomena that have revolutionized our understanding of the universe. Dark matter is a form of matter that does not interact with light or other forms of electromagnetic radiation, making it invisible to traditional observation methods. Its presence is inferred from its gravitational effects on visible matter and the large-scale structure of the universe. Scientists believe that dark matter makes up about 85% of the total matter in the universe, while ordinary matter, stars, planets, and galaxies accounts for only about 15%. Despite its prevalence, the exact nature of dark matter remains elusive. Various lines of evidence support the existence of dark matter. One compelling piece of evidence comes from observations of galactic rotation curves. According to the laws of gravity, stars and gas on the outskirts of galaxies should move slower than those closer to the galactic center. However, observations have shown that stars maintain a relatively constant velocity, suggesting the presence of unseen mass, dark matter, providing the additional gravitational pull. Other evidence comes from gravitational lensing, where the bending of light around massive objects indicates the presence of unseen matter. Additionally, the cosmic microwave background radiation, the leftover radiation from the early universe, provides information about the distribution of matter and supports the notion of dark matter. Scientists have proposed various particle candidates for dark matter, including weakly interacting massive particles and axions. Experiments such as the Large Underground Xenon Detector and the search for particle collisions in the Large Hadron Collider aim to directly detect these elusive particles. While dark matter is responsible for the gravitational effects observed in the universe, dark energy is a mysterious force driving the accelerated expansion of the universe. First discovered in the late 1990s through observations of distant supernovae, dark energy accounts for approximately 68% of the total energy in the universe. Dark energy manifests as a repulsive force that counteracts gravity's attractive force, causing galaxies to move away from each other at an accelerating rate. The exact nature of dark energy remains unknown, and it poses one of the most significant challenges in modern cosmology. One possible explanation for dark energy is the cosmological constant, introduced by Albert Einstein himself. It posits that empty space possesses a constant energy density, which contributes to the observed acceleration. Another hypothesis is that dark energy arises from a dynamic field permeating the universe, often referred to as quintessence. Scientists are using various observational techniques to study dark energy, including the study of supernovae, the measurement of large-scale galaxy clustering, and cosmic microwave background observations. The European Space Agency's Euclid mission and and the Dark Energy Spectroscopic Instrument are among the upcoming projects aimed at shedding more light on dark energy. Black holes are regions in space where gravity is so intense that nothing, not even light, can escape their grasp. They are formed from the remnants of massive stars that have undergone a gravitational collapse, resulting in an incredibly dense and compact object. The defining feature of a black hole is its event horizon, the boundary beyond which no information or matter can escape. Beyond the event horizon, the gravitational pull becomes infinitely strong, leading to a phenomenon called gravitational singularity. This singularity is a point of infinite density and zero volume, where our current understanding of physics breaks down. It is here that the laws of physics, as we know them, no longer apply. Black holes have several intriguing properties. One of them is their ability to warp the fabric of spacetime. This bending of spacetime results in a phenomenon known as gravitational time dilation, where time appears to slow down near a black hole compared to distant observers. Black holes also have an associated property called Hawking radiation, named after physicist Stephen Hawking. According to quantum field theory, even black holes are not completely black. They emit a faint radiation due to quantum effects near the event horizon, resulting in a slow loss of mass and energy over time. This phenomenon has significant implications for the ultimate fate of black holes. Researchers have made significant progress in observing and understanding black holes. In 2019, the Event Horizon Telescope collaboration captured the first ever direct image of a black hole silhouette, specifically the supermassive black hole at the center of the M87 galaxy. This groundbreaking achievement provided visual confirmation of the existence of black holes, aligning with the predictions of Einstein's general theory of relativity. Beyond visual observations, scientists also study black holes through various means, including gravitational wave astronomy. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects. Laser Interferometer Gravitational Wave Observatory and other gravitational wave detectors have successfully detected gravitational waves originating from the mergers of black holes. These detections offer valuable insights into the properties and behavior of black holes. Black holes play a crucial role in our understanding of the cosmos. They contribute to the growth of galaxies, influence the distribution of matter, and shape the structure of the universe. Moreover, black holes are connected to the ultimate fate of the universe. Depending on their size and properties, black holes can evaporate over time due to Hawking radiation, potentially contributing to the long-term evolution of the cosmos. The multiverse theory proposes that our universe is just one of many universes existing alongside each other in a vast cosmic ensemble. Each universe within the multiverse may have its own set of physical laws, constants, and initial conditions, resulting in a wide range of possible realities. There are several different types of multiverse theories, each with its own distinct characteristics. One popular concept is the inflationary multiverse, which arises from the theory of cosmic inflation. According to this idea, during the early moments of our universe's expansion, different regions underwent rapid inflation, creating bubble-like universes within a larger multiverse. Each bubble universe possesses its own unique set of physical properties. Another multiverse concept stems from string theory, a theoretical framework that aims to unify the fundamental forces and particles of the universe. In this scenario, known as the brane multiverse or parallel brane theory, our universe is likened to a three-dimensional brane floating within a higher-dimensional space. Other branes, representing parallel universes, may exist alongside ours, separated by vast distances in the higher-dimensional bulk. The concept of the multiverse has profound implications for our understanding of reality. It raises the possibility that the fundamental constants of nature and the laws of physics could vary across different universes. This variation could help explain the fine-tuning of our universe's physical parameters, suggesting that our existence may be a result of the specific conditions in our particular universe. The multiverse theory also addresses the question of the anthropic principle. The anthropic principle states that the observed properties of the universe are conducive to the emergence of life and conscious observers. In the context of the multiverse, the anthropic principle suggests that we find ourselves in a universe suitable for life because life can only exist in those specific universes capable of supporting it. However, it is essential to note that the multiverse theory is highly speculative and currently lacks direct empirical evidence. Since other universes are beyond our observational reach, testing the multiverse hypothesis poses significant challenges. Cosmic inflation theory proposes that within a fraction of a second after the Big Bang, the universe underwent an exponential expansion, expanding faster than the speed of light. This rapid expansion smoothed out irregularities in the distribution of matter and energy, leading to the remarkable uniformity and isotropy observed on large scales in the universe today. One of the primary motivations for cosmic inflation theory is to explain the observed properties of the cosmic microwave background radiation. The cosmic microwave background radiation, a faint radiation left over from the early universe, exhibits a remarkably uniform temperature in all directions. However, without cosmic inflation, it would be challenging to explain how regions of the universe that were once in close proximity ended up having similar temperatures, as they would not have had enough time to exchange energy and reach thermal equilibrium. Scientists have put forth several theoretical mechanisms to explain cosmic inflation. One of the earliest and most influential proposals is the inflationary model by physicist Alan Guth. According to this model, a hypothetical field called the inflaton experienced a temporary phase of rapid exponential expansion, driving the inflationary period. As the inflaton field settled into its stable state, the energy released during this process initiated the hot Big Bang phase. Other models, such as the chaotic inflation model and the new inflation model, have also been proposed, each with their own variations and predictions. These models introduce different types of scalar fields that drive inflation and provide explanations for the observed uniformity and flatness of our universe. While cosmic inflation theory provides a compelling explanation for various cosmic observations, it also raises new questions and challenges. For example, the exact nature of the inflaton field and its properties remain unknown. The theory also requires fine-tuning of initial conditions to achieve the observed universe's characteristics, leading to the so-called fine-tuning problem. The nature of dark energy remains one of the most profound mysteries in modern physics. Two main hypotheses attempt to explain its origin and properties: the cosmological constant and dynamic field theories. The cosmological constant, originally introduced by Albert Einstein, posits that dark energy arises from a fundamental property of empty space itself. According to this idea, even in the absence of matter and radiation, space possesses a constant energy density that drives the observed accelerated expansion. This concept implies that dark energy remains constant over time and across space. On the other hand, dynamic field theories propose that dark energy arises from a yet unknown field permeating the universe. This field, often referred to as quintessence, varies in strength and properties as the universe evolves. Unlike the cosmological constant, dynamic field theories allow for the possibility that dark energy changes over time and can interact with other fields and matter. Theoretical models attempt to describe the behavior of dark energy by postulating the existence of scalar fields with specific potential energy functions. The dynamics of these fields determine the properties and evolution of dark energy. Different potential energy functions lead to distinct behaviors, including scenarios where dark energy weakens or grows stronger over time. The nature of dark energy has profound implications for the ultimate fate of the universe. If dark energy remains constant or weakens only slightly over time, the universe's expansion will continue to accelerate, ultimately leading to a Big Rip scenario. In this scenario, the accelerating expansion becomes so strong that it tears apart galaxies, stars, and even fundamental particles, resulting in the universe's complete dissolution. However, if dark energy becomes stronger over time or exhibits more complex dynamics, other outcomes are possible. These include scenarios where dark energy causes the universe to collapse or leads to the formation of new structures, such as galaxies, even in the presence of accelerating expansion. The question of whether we are alone in the universe has intrigued humanity for centuries. With billions of galaxies, each containing countless stars and potentially habitable planets, the odds of finding extraterrestrial life seem promising. However, the search for life beyond Earth is a complex endeavor that requires careful investigation and scientific rigor. One approach to the search for extraterrestrial life focuses on the exploration of our own solar system. Missions to Mars, such as the Mars rovers and the upcoming Mars Sample Return mission, seek signs of past or present microbial life on the red planet. Scientists examine the Martian terrain, search for water, and analyze the composition of rocks and soil to gather clues about the potential existence of life. Beyond Mars, other celestial bodies within our solar system, such as Saturn's moon Enceladus and Jupiter's moon Europa, show evidence of subsurface oceans. These moons offer intriguing environments that could potentially harbor microbial life. Future missions, like the Europa Clipper, aim to study these moons in detail, including analyzing plumes and conducting subsurface exploration. Another approach in the search for extraterrestrial life involves the study of exoplanets, planets orbiting stars outside our solar system. The Kepler and TESS missions have discovered thousands of exoplanets, some of which are located within their star's habitable zone, a region where liquid water could exist on the planet's surface. Scientists analyze the composition of exoplanet atmospheres for biosignatures, such as the presence of oxygen, methane, or other molecules indicative of life. In addition to direct exploration, researchers utilize telescopes to search for signs of intelligent extraterrestrial civilizations. The search for extraterrestrial intelligence employs radio telescopes to listen for potential signals emitted by advanced civilizations. These searches target specific frequencies or patterns that could indicate intentional communication. The discovery of phosphine gas in the atmosphere of Venus has sparked excitement and further investigation. While phosphine can have non-biological origins, its presence in the atmosphere of Venus raises the possibility of microbial life thriving in the planet's cloud decks. Future missions, like NASA's planned Veritas and Da Vinci Plus missions, aim to study Venus in more detail, providing insights into its potential habitability. Additionally, advances in astrobiology and synthetic biology enable scientists to investigate the limits and conditions for life as we know it. They study extremophiles, organisms that thrive in extreme environments on Earth, to understand the potential habitability of similar environments elsewhere in the universe. One possible fate of the universe is eternal expansion. If the observed accelerated expansion driven by dark energy continues unabated, the universe could expand indefinitely. In this scenario, galaxies would gradually become more distant from each other, and the universe would grow increasingly sparse and cold over time. This fate is often referred to as the Big Freeze or the heat death, where the universe eventually reaches a state of maximum entropy. Another potential fate is the Big Crunch. In this scenario, the gravitational pull of matter in the universe overcomes the expansion driven by dark energy, causing the universe to eventually contract. The universe would collapse in on itself, leading to a dense and hot state similar to the Big Bang. This fate is characterized by a reversal of the expansion, with galaxies, stars, and even fundamental particles being compressed to an unimaginable density. Additionally, there is the possibility of a big rip. If dark energy becomes stronger over time or exhibits more complex dynamics, it could lead to an accelerated expansion so powerful that it tears apart galaxies, stars, and even fundamental particles. In this scenario, the universe would be torn apart in a cataclysmic event, resulting in the complete dissolution of all cosmic structures. It is important to note that the fate of the universe is still a topic of active research, and our current understanding is limited. The ultimate destiny of the cosmos depends on the precise nature of dark energy, which remains enigmatic. Further observational data and theoretical advancements are necessary to provide more conclusive insights into the fate of our universe. One possible way to gain insights into the fate of the universe is through the measurement of the universe's geometry and density. The curvature of space and the density of matter and energy play crucial roles in determining the future evolution of the universe. Ongoing observations, such as those carried out by the European Space Agency's Euclid mission, aim to precisely measure these quantities and shed light on the fate of our cosmos. Additionally, the study of the large-scale structure of the universe and the properties of dark matter and dark energy provide valuable clues. By analyzing the distribution of galaxies, the growth of cosmic structures, and the behavior of dark energy, scientists hope to refine our understanding of the universe's future. It is important to acknowledge that our current understanding of the fate of the universe is based on the known laws of physics and the data available to us. However, the possibility of new discoveries, unexpected phenomena, or paradigm-shifting theories cannot be ruled out. Future breakthroughs could revolutionize our understanding and lead to new predictions about the destiny of our vast cosmos. These enigmas continue to push the boundaries of human knowledge. While we may not have all the answers yet, the pursuit of understanding is what fuels our curiosity and drives scientific exploration. Thank you for joining me on this incredible journey through the unknown. Don't forget to like, share, and subscribe to our channel for more mind-expanding content.